This is paper 2, November 2010 for the standard level, A1, and it's your usual data analysis question. That's the start of every paper 2 question. So a student performs an experiment with a paper toy that rotates as it falls slowly through the air. After release, the paper toy quickly attains a constant vertical speed as measured over a fixed distance. So dropping it over here, in this time period over here, it gets to a constant speed, and then over this fixed distance here, the time is measured. The aim of the experiment was to find how the terminal speed of the paper toy varied with its weight. The weight of the paper toy was changed by using different numbers of paper sheets in its construction. Okay, so that's the background to this data that we're going to analyze, and we've got this over here, and it says the graph shows the points shows a plot of the terminal speed v of the paper toy calculated from the raw data and the number of paper sheets n used to construct the toy. The uncertainty in v for n is equal to 1 is shown by the error bar. So we've got an error bar over there. The fixed distance is 0.75, so that's your fixed distance, and has an absolute uncertainty of 0.01 meters, and the percentage uncertainty in the time taken to fall through the fixed distance is 5%. Calculate the absolute uncertainty in the terminal speed of the paper toy for n is equal to 6. So we're looking at this point over here, which, if you look at it carefully, it is going through your 0.4 mark. Okay, so we obviously are going to, I've got my data booklet open here at the correct place. We're going to be looking at that. We have got for the speed, v is equal to distance over time, like that. So according to this formula, if I wanted to work out the absolute uncertainty in the terminal speed, I would use this, that my change in my absolute uncertainty in v over v would equal to my absolute uncertainty of d over d plus my absolute uncertainty of t over t. Now, we are told here that for a fixed distance 0.5, we have an absolute uncertainty there of 0.01, so that's going to be 0.01 divided by your d, which was 0.75, plus. Now for the time, we're actually given a percentage. I've actually taken it out there, but notice here that we're given a percentage. Now, this, when you have your absolute divided by your time, you get a relative uncertainty. And when you times that by 100, you get your percentage. So if I wanted to go from 5% back to my relative uncertainty, which is this over here, obviously I just put that 5 over 100, so I'll get 0.05. So I'm going to get this part over here would be 0.05. I've got my change in v, and we know from here that our velocity is actually given to us for that one of 0.4. So I'm going to put 0.4 in there like that. So my change in v is going to equal 0.4, 0.01 over 0.75 plus 0.05. And when we do that calculation, when you put that into your calculator, you will get 0.025 meters per second to the minus 1. That's this value over here. So I've done the working over there. Okay, I hope you follow that. It was a bit difficult because they use a combination of different things, and you also had to think of your formula for your velocity. So on the diagram, draw an error bar on the point corresponding to n is equal to 6. So we want to put this value in here. Now firstly, we've got to be careful with our scale. Now, how much is each one of these small little blocks here? if I go from one small block to another small block here, we see that we've got 5 space, we're going to 0.5, so the small block is 0.01. So I'm going to have basically 2.5 small blocks on either side here. Now, my board is probably, where I'm writing, is probably not going to be all that accurate, so we'll try. But I've got to go down basically 2.5 blocks either side of there. I don't know how accurate that is. That doesn't look very accurate. Hopefully you, using a pencil and ruler and on your diagram, will give a much better. But you're going 2.5 either way from that point over there, because that would be your plus minus value. And then it says, on the graph, draw a line of best fit. Now, as per usual here, we've got to, when it says a line, it doesn't need to be a straight line. And in this case over here, we can see that it's not a straight line. I mean, there's not possible here. It seems to be curving around. So any reasonable curve that where it goes through all your error bars. So we would do something like that. Would give us our value. Okay. Now, it next says over here, the student hypothesized that V is proportional to N. Use the data points for N is equal to 2 and N is equal to K from the graph opposite to show that this hypothesis is correct. Now, whenever you have a proportional graph, if I've got V is proportional to N, that means that V is equal to some constant Kn, or V over N is equal to a constant. So what we've got to do is we've got to take our values for V and N. We need to take it for N is equal to 2 and N is equal to 4. And we've got to divide the two and see if they come to a constant K. So let's do for N is equal to 2. We're going to get our V for N is equal to 2 is going to equal to 0.24. You must just check to see whether I'm doing this right. 0.24 divided by 2, and that is for when N is equal to 2. And for N is equal to 4, we're going to have 0.34 divided by 4. Now, when you do that, this gives you 0.12, and this gives you 0.085. So we can clearly see that you're not getting a constant value in each case, and therefore not proportional. Okay, so going on to the next question over here. It says, another student hypothesized that V might be proportional to the square root of N. To verify this hypothesis, he plotted a graph of V squared against N as shown below. So let's just see this. He's saying that V is proportional to K. Well, let's don't put the K in yet. We only do it when you've got an equal sign. To the square root of N. Therefore, V is equal to some constant square root of N, and squared both sides, we're going to get V squared is equal to a new constant. I'll call it capital K N. And so plotted now V squared against N. So explain how the graph verifies the hypothesis that V is proportional. Well, to get a proportional graph, it always needs to go through the origin and it needs to be a straight line. And this does both. So our graph goes through the origin, through 0, 0, and it's a straight line. And therefore, it is a proportional graph. You could do the same thing as before. You could, if we took that value and we divided them, and we took that value and we divided them, they should always equal to this constant value K here.